And we have a special setup today. We share the session, looking a little bit, obviously, what you guys all see on the room and how facilities could look like or be affected by that. I will talk a little bit about a larger hyperscale specification, something that we want to put out quite soon. The first one after Meta in 2011. Perfect. There we go. So. We have one missing. Peter is not with us today, but I'll talk a little bit on his behalf. Of course, we have a little bit of a special sauce for those new DC world. What is the new requirement? Everybody's talking about it. We have a massively different requirements for the density, for the air cooling, for the liquid cooling. Air cooling, bad air cooling concepts are going even faster out of fashion than before. That's probably what Daniel can talk a little bit about. And we need, so my deep conviction is that we need data centers going from data fortresses, nobody gets in, nobody gets out, to integrated partners for energy systems. And there is a need to explain how those data centers look like, because the last one spec in that field was relatively old. So this is something we came up with. The data center historians from you would maybe recognize this shape, this so-called Yahoo chicken cube. We fact-checked, the patents run out. So we make wild use of that, because it is a very, very efficient air-cooled facility. We add a couple of things to it. So low adiabatic usage. Obviously, I'm running wooden data center. There's wooden construction in there. Rainwater collection for this cooling to have that efficient, and not only the heat reuse component. There's integrated heat pumps, but also a bidirectional, microgrid or cogeneration or whatever you have. That is what we want to look into. So this, everybody has seen those racks. You have it more real and more grabbable on the shop floor, but the requirements, went up quite a bit, and they are going to be increased. Well, the interesting information that I put in here last minute is the 400 volt DC on the bus bar side. So we're going up in voltages 12, 48, 54, and now we're at 40 volts. And so the next iteration will be powered by a lot of high voltage DC. And there is a way to do the whole data center in DC with a drastically simplified setup. You see there is now one DC-DC converter just in front of the rack. That obviously would be even that would be dropped in the case of a 400 volt DC supply. This we designed with 48 volts in mind, but the top one, the traditional one, has a lot of steps, transitions, transformers, and a lot of inefficiencies, some of which the OCP already tackled. But going superconductive becomes a more and more viable option. The requirements that we were looking in for, we could publicly get, is that you have, I think it's 48 volts, but it's probably 54 volts on that bus bar. So probably a little lower than 2 kiloamps of amperages, so quite a lot. So if you combine all of that, you have 14 ports with 180 amps of kilowatts. So that's the total amperage in this facility, which is just what had been done in superconductivity right now. So this is how we set that up. The big introduction step is the rectifiers in the beginning. You can have centralized battery connects again, because when a superconductor busbar, you can move energy, without real resistance, and especially without losses. And so this is a way to power this quite efficient, and this is how a superconductor is looking like. and we want to look into the comparison of AC and DC or superconductive DC systems within the spec. Another thing that I really like to do out of my work in the MDC is to use the appendixes to go into deep dives. We will look into heat reuse, we will look into timber construction. On code generation, we can really go into the detail for the spec. And on the superconductive comparison versus AC distribution. The interesting part, it has become quite viable with the voltages, with the density that we see. The return of the invest is, around 15 months for a superconductive system. So it's something that we, as an industry, might need to look into a little bit more. And with that, I hand over to Daniel.
Thank you, Karl. I hope you can hear me okay. So Modular Data Center Group update is work has been published on liquid-cooled modular data centers. Some white papers will be forthcoming. Reviewed by the MDC Group and will be published with a rework spec for AI, let's just say. So let's just talk about the big elephant in the room. That's why we're all here. We're all here to learn about AI and how AI is going to change our world. But the big elephant is it's all about power. Power is everything. The typical brick and mortar co-location facility was built between 5 and 10 kW per rack. A little, maybe a hyperscale co-location facility is maybe built 10 to 20 kW per rack. A supercomputer HPC is maybe built to 35 kW per rack. We're talking about power that's going to be in the 120, 130, 140 kW per rack. Data centers just aren't built to sustain that kind of power. I've done a project many years ago where we had to retrofit a data center for electrical purposes. It took 9 months. You had to unplug absolutely everything. You're going to interrupt customers being able to do business, operations, collecting rent. You're going to have to set expectations for how long. It may take 2 years to get the power company to bring additional power, or if you think about if you got 10 racks in a row in a co-location facility that's 10 kW per rack, now you're going to have one rack that's going to take up all the power and probably all the networking. So the challenges of the NVIDIAs is a whole paradigm shift. Direct liquid cooling, getting enough chiller systems, getting enough generators out there to take care of that. You're going to have UPS for the liquid cooling chillers. All that is going to be a paradigm shift. And the current supply chain isn't really ramped up to handle this type of demand in this short order. This is our concept, not everybody can afford or be a Meta or a Microsoft or Amazon. This is a 4-rack modular data center. Runs on adiabatic cooling, gives you 35 kW per rack. And then there's liquid cooling to take up the additional. Data centers, to be very, very efficient in adiabatic cooling, can be as low as 1.02, 1.03. When you add the chilled water, it's going to get 1.15, 1.2, somewhere down the road. But this is something that can come up in 90 days. So when you order your Blackwell, it's going to take you more than 90 days to get that. You could be building your modular data center. You could be retrofitting everything on your data center floor, or you can put it out in the parking lot. But you can be up and running, little or no impact to the operations of your existing data center, and just continue to run. So we also have direct-to-chip liquid cooling. What that would look like, temperature increases, chip performance. So the advantages of modular data centers is everything is about energy. The more energy you can utilize to power your IT infrastructure versus everything else, it's going to be a lot easier on your budget. fully prefabricated. Everything is manufactured in a facility, assembled, tested, disassembled, shipped to the site, and reassembled in a short amount of time. That 4-rack unit can come up in as little as 5 days. High density in that 4-rack unit is 120 kW per rack, 500 kW. Everything is digitalized. The PLC, you can sit at your desk, learn about everything, monitor everything. Flexible expansion. So let's say today you order 4 racks or 5 racks or 10 racks, and you decide 6 months from now you want another 10 racks. We manufacture, ship it to the site, basically refurbish the wall and connect the other one, and you're up and running now with 20 racks. Low OpEx. Little or no water used, even for adiabatic cooling. Electricity can expand along as well. So this is what a hyperscale modular data center would look like. In this picture here, we have actually 80 racks at 150 kW per rack, and this could come up in probably 120 days. Reducing the amount of electrical and cooling required. All users can leverage direct liquid chip or direct cooling, as well as the adiabatic cooling. So we have a call to action.
Yes. So, gave him a quick overview. We invite you to our group work, where we can go into a lot more detail. I'm really excited about the opportunity for this learning platform to maybe go on webinar on even only parts of the spec. But yeah, happy to invite you to the modular group calls and the data center facility group calls, and check out for the spec. As you've seen, we were a bit optimistic for September, but it will be happen in 2024. And with that, we have we open up the room for questions.
Todd Kazmersky with Fourier Earth. I'm wondering where the constraint for the 380 volts or 400 volt DC bus comes from, because it seems like with a 400 to 480 volt 3-phase AC system, it's more natural to go to a higher voltage. So why not 800 or 900 volts DC?
The interesting thing is there is no standardization, and so 380 is basically the 380 volt requirements. As far as I understand, what's most plausible to me is that there were DC-DC power supplies available for servers with that voltage, which was an optimum out of the non-superconductive world. The superconductor is there 2 ways. They either try to go down as low as possible to run the whole 100 megawatts, 100 or 100, 200 megawatts on 48 volts. That is also an option that it can do, but obviously then you have really big tap-offs. Because there is no electric and with intelligent design very little magnetic resistance, you don't need high voltages, but you're free to choose your voltage. It's absolutely no standardization. You can go on 350 and a half or 900 or 1000. The technical range is something, I think, between 250 and 1500. There are a lot of those applications around. So 380 volts, we were lucky now to hit apparently the next rack specification. So I think the 400 volt is something still an optimum for this.
Okay, thank you.
So I just have an amateur question. So for DC distribution, right, superconductor is the only way, or there's some other?
No, there are other ways. So we are fortunate to have now for every size of data center. We as Woodendatacenter, we also have a DC option, and up to a megawatt, it's quite viable to go with traditional bus bar. And between a megawatt and 20 megawatts, there is the option of medium voltage DC. So mine is plus 1500. There was an interesting presentation I'll like you to look up in Lisbon, where somebody talked about medium voltage distribution of DC. But that are the options. So that is something that people are now looking into. And there's also ways to combine this, having some parts superconductive, having some parts medium voltage there. I know that the Hyperscale are looking on different levels of distribution for DC, how they want to solve it. We just present the most extreme, nearly superconductive till the rack, but there are alternatives to that.
Any other questions? If not,
Thank you.
Thank you very much.
Thanks.